This is Harshit Partney, roll number 201501101107, and this is the third topic in the video, explanation of the direct and indirect bandgap semiconductors using EK diagrams. First of all, I will talk about direct bandgap semiconductor. In a direct bandgap semiconductor, the top of the valence band and the bottom of the conduction band occur at the same value of momentum. In a direct bandgap semiconductor, a direct recombination takes place with the release of the energy equal to the energy difference between the recombining particles. The probability of a radiative recombination is also very high. The efficiency factor of a DBG semiconductor is higher. Thus, DBG semiconductors are always preferred over indirect band semiconductors for making optical sources. Examples of direct bandgap semiconductors are gallium, arsenide, etc. A photon of energy Eg, where Eg is the bandgap energy, can produce an electron-hole pair in a direct bandgap semiconductor quite easily because the electron does not need to be given very much momentum. However, an electron must also undergo a significant change in its momentum for a photon of energy Eg to produce an electron-hole pair in an indirect bandgap semiconductor. This is possible, but it requires such an electron to interact not only with the photon to gain energy, but also with a lattice vibration called a phonon in order to gain gain or lose either momentum. This is the diagram which shows the difference in band gap between conduction and valence band in direct band gap semiconductors. Indirect band gap semiconductors. An indirect band gap semiconductor is one in which the maximum energy level of the valence band and the minimum energy level of the conduction bands are misaligned with respect to momentum. In case of indirect band gap semiconductor, due to a relative difference in the momentum, first the momentum is conserved by release of energy, and only after both the momenta align themselves a recombination occurs accompanied with a release of energy. The probability of a radiative combination is comparatively low, as here the process is mediated by a phonon. The efficiency factor of indirect bandgap semiconductor is also lower. Examples of IBG semiconductor are silicon, germanium, etc. The indirect process proceeds at a much slower rate as it requires three entities to intersect in order to proceed: an electron, photon, and a phonon. This is analogous to chemical reactions, where in a particular reaction step, a reaction between two molecules will proceed at a much greater rate than a process which involves three molecules. This is a diagram for band gap between valence band and conduction band of indirect band gap semiconductors. A common and simple method for determining whether band gap is direct or indirect uses absorption spectroscopy. By plotting certain powers of the absorption coefficient against photon energy, one can normally tell both what the values does the band gap has and whether or not it is direct. As a result of such considerations, gallium arsenide and other direct band gap semiconductors are used to make optical devices such as LEDs and semiconductor lasers, whereas silicon, which is an indirect band gap semiconductor, is not suitable for optical devices.